Hi students, today we'll be discussing part 3 of module 2. In the previous two sessions, the basic concepts of fast Fourier transform including DIT-FFT and DIF-FFT was covered. In this session, we learn the applications of FFT, which includes efficient computation of DFT of two real sequences and efficient computation of DFT of a two endpoint real sequence. First, we'll discuss the efficient computation of DFT of two real sequences. We know that the FFT algorithm performs complex multiplications and additions even though the input data may be real due to the phase factors or the total factors. Here, we are going to use FFT for the computation of DFT of two real-valued sequences using a single DFT. We consider x1 of n and x2 of n to be two real-valued sequences of length capital N. And using this x1 of n and x2 of n, we form x of n, which is a complex valued sequence given by x of n is equal to x1 of n plus j into x2 of n. Since DFT is linear, x of k can be written as x of k is equal to x1 of k plus j x2 of k. Now we express x1 of n and x2 of n in terms of x of n. Since x1 of n is a real part of x of n, it can be written as x of n plus x conjugate of n by 2. And since x2 of n is the imaginary part of x of n, it can be written as x of n minus x conjugate of n by 2j. On taking the DFTs of x1 of n and x2 of n, we get x1 of k is equal to 1 by 2 into DFT of x of n plus DFT of x conjugate of n. Similarly, x2 of k is equal to 1 by 2j DFT of x of n minus DFT of x conjugate of n. By the complex conjugate property of DFT, we know that DFT of x conjugate of n is equal to x conjugate of capital N minus k. Therefore, using this substitution in the previous two equations, we get x1 of k is equal to 1 by 2 x of k plus x conjugate of n minus k, where x of k is a DFT of x of n and x conjugate of n minus k is the DFT of x conjugate of n. And x2 of k is given by 1 by 2j into x of k minus x conjugate of n minus k. So, by calculating only one DFT, which is x of k, and using a few computations for x conjugate of n minus k, we have found out two DFTs, which are x1 of k and x2 of k. This is how we perform a single DFT on the complex valued sequence x of n and obtain DFTs of the two real sequences x1 of n and x2 of n. We look into an example to compute the 4-point DFT of two real sequences x1 of n and x2 of n using a single 4-point DFT. Our sequences are given by x1 of n and x2 of n. Now, we are going to combine x1 of n and x2 of n to form a complex valued signal given by x of n is equal to x1 of n plus j into x2 of n, which is given by 1 plus 2j, 2 plus 2j, j and 1 plus j. Next, we are going to find the 4-point DFT of the sequence x of n. The 4-point DFT can be found out either by using decimation in time or decimation in frequency FFT algorithm. In order to compute the 4-point DFT, we require the twiddle factors given by Wn. Since we are finding the 4-point DFT using FFT, we need to find out W4 raised to 0 as well as W4 raised to 1. We are going to use the DIT FFT to find x of k. I've drawn the DIT FFT structure to compute a 4-point DFT. The structure for DIT has already been discussed in section 1 of module 2. Since we are using DIT, the inputs are in the bit reversed order. So, the inputs are marked as x of 0, x of 2, x of 1 and x of 3. Since we are finding a 4-point DFT, there are two stages. The first stage is the 2-point DFT and the second stage is the 4-point DFT. First, we'll compute the outputs of the first stage. Coming to the first output sample, we are going to have 1 plus 2j at this branch and j into W4 raised to 0 from the other branch. These two samples add up, that is 1 plus 2j plus j, and the output becomes 1 plus 3j. Similarly, the next sample value, we are having 1 plus 2j from this branch and j into W4 raised to 0 into minus 1, which is minus j from the other branch. So these two add up to give 1 plus 2j minus j, which is 1 plus j. Similarly, the other output samples can also be found out as 3 plus 3j and 1 plus j. The next stage is the 4-point DFT. The 4-point DFT can also be computed by the same method. For example, we look at the first sample value. We have 1 plus 3j from this branch and we have 3 plus 3j into W4 raised to 0 from the other branch. So these two samples add up, which gives us 1 plus 3j plus 3 plus 3j, which is 4 plus 6j. Similarly, all the other three output sample values can be found out as 2, minus 2 and 2j. So, we found out the DFT samples. Once we have found out x of k, we are going to find x1 of k and x2 of k. If we look into the equation for x1 of k and x2 of k, both have the terms x conjugate of n minus k. So next, we have to find x conjugate of n minus k. Here, capital N is 4 and k can vary from 0 to 3. So, we are going to substitute values of k. When k is equal to 0, x conjugate of n minus k becomes x conjugate of 4, which can be written as x conjugate of 0, because x of k is a 4-point DFT and hence it is periodic with respect to 4. The DFT sample x of 0 is given by 4 plus 6j. So x conjugate of 0 becomes 4 minus 6j. Similarly, when k is equal to 1, we get x conjugate of n minus k as x conjugate of 3, which is equal to minus 2j. When k is equal to 2, we get x conjugate of 2, which is minus 2, and when k is equal to 3, we get x conjugate of 1, which is 2. Hence, we have found the terms x conjugate of n minus k. Now, since we have x of k and x conjugate of n minus k, we can find out x1 of k given by 1 by 2 into x of k plus x conjugate of n minus k, and x2 of k as 1 by 2j into x of k minus x conjugate of n minus k. So, these are the answers for x1 of k and x2 of k. So, by simply finding one 4-point DFT, which is x of k, and by substitutions to find x conjugate of n minus k, we have found out two 4-point DFTs, x1 of k and x2 of k. Next, we look into the efficient computation of DFT of a 2n point real sequence. Here, we consider g of n to be a real valued sequence of 2n points. The 2n point DFT of g of n can be obtained from the n point DFT of a complex valued data. So first, the 2n point real sequence g of n is divided into two real sequences x1 of n and x2 of n, each of n samples. x1 of n is given by g of 2n and x2 of n is given by g of 2n plus 1. Here, g of 2n represents the even numbered samples and g of 2n plus 1 represents the odd numbered samples. We are going to combine x1 of n and x2 of n to form a complex valued sequence given by x of n is equal to x1 of n plus j into x2 of n. Next, we represent x1 of n and x2 of n in terms of x of n. Since x1 of n is the real part of x of n, it is given by x of n plus x conjugate of n by 2. And since x2 of n is the imaginary part of x of n, it is given by x of n minus x conjugate of n by 2j. The DFTs of x1 of n and x2 of n are given as x1 of k is equal to 1 by 2 into DFT of x of n plus DFT of x conjugate of n, and x2 of k is equal to 1 by 2j DFT of x of n minus DFT of x conjugate of n. According to the complex conjugate property, we know that DFT of x conjugate of n is equal to x conjugate of n minus k. Substituting this in the previous two equations, we get x1 of k is equal to 1 by 2 into x of k plus x conjugate of n minus k, and x2 of k is equal to 1 by 2j into x of k minus x conjugate of n minus k. Here, x of k is a DFT of x of n. Now, once we've got the two n-point DFTs, x1 of k and x2 of k, we are going to represent the 2n-point DFT, which is g of k, in terms of x1 of k and x2 of k using DIT FFT expression. So, the 2n-point DFT of the sequence g of n is given by g of k is equal to summation n is equal to 0 to 2n minus 1 g of n w2n raised to nk. Now, we are going to split g of n into even numbered samples and odd numbered samples, each of which will have n points. Hence, the equation can be rewritten as summation n is equal to 0 to n minus 1 g of 2n w2n raised to 2nk plus summation n is equal to 0 to n minus 1 g of 2n plus 1 w2n raised to 2n plus 1 into k. Here, the first summation term represents the endpoint DFT of the even numbered sequence, and the second summation term represents the endpoint DFT of the odd numbered sequence. Rearranging this second summation, we can, in both these summations, we have a term w2n raised to 2nk. We are going to make a modification for this term. We know that wn raised to 2 is equal to wn by 2. So w2n raised to 2nk becomes wn raised to nk. Substituting this in the equation for g of k, we get g of k as follows. We already know that x1 of n is equal to g of 2n, which are the even numbered sequences, and x2 of n is equal to g of 2n plus 1, which are the odd numbered sequences. If we look at the two summations, we find that limits are from n is equal to 0 to capital N minus 1, and the total factors are wn raised to nk. This means that both these summations represent endpoint DFTs of x1 of n and x2 of n respectively. So g of k can be written as x1 of k plus w2n raised to k into x2 of k. But this gives us only the first n DFT samples. In order to get the next n DFT samples of g of k, according to the DIT-FFT expression, we have g of k plus n is equal to x1 of k minus w2n raised to k x2 of k. This is how from a single endpoint DFT, which is x of k, we got x1 of k and x2 of k, and from these x1 of k and x2 of k, we have computed g of k, which is the 2-endpoint DFT. We will look into an example to find the 8-point DFT of a sequence using 4-point DFT. So the sequence is given as g of n. The next step is that we split g of n into even numbered sequences and odd numbered sequences. So the even numbered sequences are given by x1 of n is equal to g of 2n, and the odd numbered sequences are given by x2 of n is equal to g of 2n plus 1. Now, using x1 of n and x2 of n, we find a complex valued signal which is given by x1 of n plus j into x2 of n. And we have the sequence 1 plus 2j, 2 plus 2j, j, 1 plus j. Now, we are going to find the 4-point DFT of the sequence x of n. This can be done by either using DIT-FFT or the DIF-FFT structure. Since we are going to find the 4-point DFTs, we require the total factors w4 raised to 0 and w4 raised to 1. Like in the previous question, we use the DIT-FFT structure to compute the 4-point DFT x of k. If we remember the previous question, we have the same x of n as that in the previous question. So, I mark the inputs in the bit reversed order as x of 0, x of 2, x of 1 and x of 3. And after computation, we get the output of the first stage as follows. And the final DFT outputs are given by 4 plus 6j, 2, minus 2 and 2j. As we did in the previous question, after finding x of k, we need to find out x conjugate of n minus k in order to calculate x1 of k and x2 of k. So, by substituting values of k from 0 to 3, we get the following values of x conjugate of n minus k. Once we have x of k and x conjugate of n minus k, we can find out x1 of k and x2 of k using the given equation. As in the previous slide, we have found out x1 of k and x2 of k, which are the 4-point DFTs. Now, from these 4-point DFTs, we are going to calculate the 8-point DFT, which is given by g of k is equal to x1 of k plus w2n raised to k x2 of k, which gives us the first 4 DFT samples, and g of k plus n is equal to x1 of k minus w2n raised to k x2 of k, which gives us the remaining 4 DFT samples. Here, k varies from 0 to 3 and 2n is equal to 8. So when we substitute k values from 0 to 3 in both the equations, we get the DFT samples G0, G1 up to G of 7. So substituting the values of k in both the equations, we get G0, G1, G2 up to G7. This is how we compute an 8-point DFT using a single 4-point DFT, which was x of k. From that single 4-point DFT, by substitutions, we calculated x1 of k and x2 of k, and using x1 of k and x2 of k, we computed g of k. This is a reference. Thank you.